Okay, so let me begin just by, I'm going to continue talking today about three manifolds, about the sort of conjectured picture of three manifolds. So let me just start by reviewing a little bit what I said at the end. I was rushing a little bit at the end last time, but remember we're looking at closed orientable three manifold, and I was discussing the case when the pi 1 of m was finite, and so remember the basic conjecture here. I'll call this conjecture A. And okay, if pi 1 of m finite, if and only if m is spherical. That was the i.e. it was it's S3 modulo some finite group G, a finite subgroup of SO4 acting freely on S3. And so I sort of I gave an account of the subgroups, the finite subgroups of SO4 that do act freely on S3, and I mentioned the observation of Seifert and Threlfall that there's always a circle action, a fixed point free circle action on S3 that commutes with the action of the group, and so it induces a circle action on the quotient, and that motivated the definition of a Seifert-Fibert space. And so one has a statement that all these spherical manifolds are Seifert-Fibert spaces, and so this is what I was trying to say right at the end, that M is spherical if and only if M is a Seifert-Fibert space with finite pi 1. And that's if and only if, in terms of the invariance, I mean, I described that with a Seifert-Fibert structure, you have a base surface, and then you have these sort of exceptional fibers with multiplicities. And so you could say that this is if and only if M has a Seifert-Fiber sort of structure with base, the 2-sphere, and, okay, well, there are sort of two cases really. There's the lens space case, so that's, I put the parentheses wrong. Okay, let's say 2 or less than or equal to 2 exceptional fibers. So that's the case of lens spaces, and I guess S3 itself, or 3 exceptional fibers with multiplicities, let's say P1, P2, P3, with, well, they correspond to these Platonic triples, so or whatever. I mean, the sum of the reciprocals is greater than 1, and remember the groups in question. And so pi 1 of m. So I was a little careless when I wrote this last. I was rushing at the end, and I didn't. Remember, you have the binary dihedral group, or you have this other sort of dihedral-like group that sort of appears, or you have the tetrahedral. Well, there were these tetrahedral-like groups. Including, so this is including T24, which is the binary tetrahedral group, and then you have the binary octahedral, icosahedral, and then again you can cross this with Zm, where M is co-prime to, well, so M, and then the order of the other factor. Okay, let me put it that way. Is 1. And the corresponding triples, so this is the group. I mean, this is pi 1 of, these are the fundamental groups that occur, right? And then the triples that occur are correspondingly, there's 2,2,N with the dihedral case, 2,3,3 with a tetrahedral case, and then 2,3,4 and 2,3,5. Okay, so that was a slightly more careful statement. That's what I was meaning to write last time. I think I forgot this factor. And remember, these stars, these are the, you take the finite subgroups of SO3, and then you just look at their inverse image back in S3. So they're okay. So that's what's supposed to happen then. Well, that's what does happen when you have spherical manifold. They're completely understood. They were classified, as I said, in the, well, the groups were classified by Hopf in the 20s, I think, and then the manifolds were identified as Seifert-Fibert spaces by Seifert and Threlfall in the 30s. And so this is completely understood. And the conjecture is that these are the only manifolds with finite fundamental group. Okay, so what happens when pi1 of your manifold is infinite? Okay, so let's look at that case. So okay, so again we're talking about, I was talking a little bit about geometric structures, and so, I mean, you know, the first, I mean, the three basic geometric structures, spherical, Euclidean, hyperbolic. So it turns out that the Euclidean manifolds in dimension 3 actually aren't that interesting. So let's look at the, I mean, Euclidean, so Euclidean 3 manifolds. Turns out there's only, I'm looking at orientable manifolds only, there's only 6. And they're all finitely covered by the 3 torus. I mean, you know, there's a general theorem of Bieberbach that, you know, I mean, the isometry group, let me just, well, so let's look at the Euclidean case. So the orientation preserving isometries of you know, the Euclidean 3 space, you know, it's just, it's a semi-direct product of the translation subgroup and, you know, SO3. So you get, it's something like this. These are the things that stabilize a point, and then you get the translation subgroup. And I guess I mean, this is true in all dimensions. There's I guess a general theorem of Bieberbach that, you know, you only have, in any dimension there's only finitely many Euclidean manifolds, and they're all finite. They all contain a z to the n, you know, a torsion-free subgroup of finite index. Geometrically, they're all finitely covered by the n torus. And so, and in dimension 2, there's only 2, of course. There's the Klein-Bottle and the torus. In dimension 3, if we just look at orientable ones, there's only 6. There are just 6, and they're all Seifert-Fibert spaces, in fact, and so they're all. Let me just for the record, just kind of write them down here. I mean, the base surface. So here's the base, and here the exceptional. Well, here are the multiplicities. Well, the exceptional fibers, the multiplicities thereof. So 1, 2, 3. Oops. 4, 5, 6. And so the first one, of course, is just a 3 torus, and then you have, so that's this one, and then let's see, you have 2, 2, 2, 2, then we have 3, 3, 3. How does it go again? 2, 4, 4, 2, 3, 6. Okay, yeah, so 2, 4, 4, and 2, 3, 6. So notice that these triples, these are the triples that add up to exactly 1, right? And then you have something over the projective plane with.
Isn't the base the 2-sphere?
Sorry, the base is the 2-sphere. Right. Thank you. Yeah.
Except for the first one.
Right. Exactly. Thank you. Right. It's a 2-sphere. Right. 1, 2, 3, 4, 5. Okay. Okay. Yeah. Thanks. Sorry. Very good. Yeah. Right. And Right. So this is the three torus. I mean, another way to describe these guys. I mean, the first five, they're all torus bundles, right, over the circle with periodic monodromy. So with monodromy of order, well, 1, that's the three torus, 2, 3, 4, and 6, respectively. So these are the only possible finite order automorphisms of the torus. Okay, so that's just for the record an account of the Euclidean manifolds. So it's not, they're just a rather small finite number of them, and they're all Seifert-Fiebert spaces, and they can be described in that way. Okay, so again, so I mean, I'm looking at the general sort of question. We're trying to say, you know, is every manifold with infinite fundamental group, you know, is it geometric? And of course we know that that's not true, but so let me just say that again. We know that if M is Euclidean, you know, or hyperbolic, then of course that implies, as I said, that the universal cover is homeomorphic to R3, and R3 is irreducible, right, by Alexander's theorem. So this is irreducible. That was the classical theorem of Alexander. And so it's not so difficult to prove that that implies that M is irreducible. So this implies that M is irreducible. So this is another homework assignment. In fact, have you got your homework? I'm collecting it now. From last time, no? Okay. So we know that the manifold M, you know, if it's going to be geometric, it's going to have to be irreducible. So you know, is the converse true? I mean, that's, you know, of course most of you know the answer, but let's approach it slowly. Well, again, historically, this is a good point to sort of mention one of the classical important theorems in three-dimensional topology, the sphere theorem, which in some sense goes away towards answering this question in some sense. So this was one of the sort of watersheds of three-dimensional topology, 1957, when Papakyriakopoulos proved the sphere theorem and Dehn's lemma, which I'll mention a little later. And so here's the sphere theorem. And as I say, this was proved by, this is Papakyriakopoulos. In 1957. He actually proved this sort of special case. Whitehead proved the full version in 1958. And incidentally, you know, I don't know if you've ever tried to read any of Whitehead's papers. He's a little hard to read, you know. In fact, apparently his students used to say that the JHC stood for Jesus, he's confusing. You know, no, that's a story about Whitehead anyway. But so here the theorem is that if you've got a three manifold, so M, a three manifold, with pi 2 M not equal to 0, then there exists an embedded sphere, an embedded two-sphere S in M, such that that embedded sphere is not 0 in pi 2 of M. So again, it's one of these very important theorems that takes sort of homotopy theoretic information, gives you very strong geometric information. And I mean, to say pi 2 of M is non-zero means that there's a map of a two-sphere into the manifold, which is not null homotopic. The conclusion is it's actually an embedded two-sphere. So this was this was a huge breakthrough, and a corollary of this, an immediate corollary of this, is that if M is irreducible, See, if every embedded two-sphere in M bounds a ball, then every embedded two-sphere is null homotopic. And so by this theorem, that implies that pi2 of M is equal to 0. Right. And so, I mean, from the point of view of sort of this question, you see, if you've got an irreducible manifold, well, could it conceivably be geometric? Well, if it is, its universal covering will have to be homeomorphic to R3. Well, this at least tells you that, that the universal covering is homotopically equivalent to R3, i.e. it's contractible. So that's an exercise, another exercise for you. So you know that pi2 is 0, and it turns out that's enough to make everything vanish just by duality. So in other words, you know, i.e., you know, M is a k pi1 space. So this was actually a huge advance. I mean, in particular, it tells you that if you take a complement of a knot in S3, then that has pi2. That's clearly irreducible by Alexander's theorem, and so pi2 of a knot complement must be 0. This is a famous problem, the asphericity of knots. And I see. Okay. Oh. Mm-hmm. Yeah, so I mean, you know, it's a great problem. I mean, if you don't have this theorem, if you try to prove, if you just draw a knot and try to prove that its complement, that pi2 of its complement is 0, I mean, it's very difficult. I mean, Whitehead was able to do it, you know, without this theorem for some special knots and so on. But in general, it's really difficult. And you know, computing pi2 of a space is really very difficult. And so this was a huge advance when it happened. Okay, so this is pointing a little bit towards perhaps the truth of this. At least the universal covering is going to have the right homotopy type. Okay, well, let's see, what else do we know? Well, we've classified the Euclidean manifolds, three manifolds. What about the hyperbolic one? So here's a sort of easy theorem that if M is hyperbolic, a hyperbolic three manifold, so I mean, you know, M is always a three manifold. I guess I'll say it. Then there can't be any Z cross Z subgroup in pi1 over M. Okay, so let me quickly sketch the proof of this. So the idea, so remember what's a hyperbolic manifold? It's one that's based on, you know, it's a quotient of hyperbolic 3 space by some group of isometries acting freely and so on. So hyperbolic 3 space, you can think of that as just the open ball, three-dimensional ball, and you know, geodesics are just circles, Euclidean circles, you know, orthogonal to the boundary, and so and one can show that the orientation preserving isometries of hyperbolic 3 space, they can be identified with the Möbius transformations of the sphere at infinity, the sort of ideal boundary of hyperbolic 3 space. So this is just isomorphic to PSL2C. So that's just, you know, this is just the conformal maps, whatever, the Möbius transformations of the sphere at infinity, which we just think of as the complex plane with the point at infinity. So that's the isometries. And now suppose you have a okay, well, let's go over here. Suppose you have a Z cross Z. Well, first of all, what are the isometries of? I mean, one. So any isometry of any element of, let's say, the orientation preserving isometries of H3 is either Okay, so there are three kinds of isometries: the hyperbolic ones, the parabolic ones, and the elliptic ones. Okay, so it's either hyperbolic. So that means that, well, one way to say that is there are two fixed points, but at infinity. So there are two fixed points. The sphere at infinity, of course, isn't really there in hyperbolic space, but every isometry naturally extends. So the picture of a hyperbolic isometry is that you have some sort of axis like this, and these 2 points are fixed, and the isometry just sort of shifts things along this, possibly twisting. I guess the old word for this was loxodromic or something. So that's a hyperbolic isometry. And then, or you could have, it could be parabolic. So they're the ones that have one fixed point on the sphere at infinity. So the picture there is that, well, you have some sort of, I'll draw another model in a minute, but you have some horosphere like this, and you're just kind of moving things sort of around like this. So there's one fixed point. And then the elliptic ones don't concern us here, because the elliptic ones, they have fixed points. They actually have fixed points in the interior, in hyperbolic space itself. And if we're dealing with with a manifold which is hyperbolic, then of course the group is acting without fixed points. So the elliptic ones needn't worry us. And so now we're trying to show that you can't have a z cross z. Well, why is that? So let's see. Suppose, suppose you have two elements of and suppose they commute, right? Well, you see, if one of them is hyperbolic, let's say, suppose alpha is hyperbolic, then it's easy to see that if beta commutes with that, then beta has to have the same fixed points as alpha. I mean, just write it down. Alpha beta is beta alpha. And so it has to have the same axis. And so you would actually get, so therefore, so alpha beta equals beta alpha implies beta hyperbolic, same axis. And so if you had a z cross z, in your fundamental group, then you'd have a z cross z, in this, there would be two commuting isometries, and they'd have the same, if one of them was hyperbolic, the other would be as well, and they'd have the same axis. And so just restricting to that axis, you'd get a z cross z subgroup of, the isometries of the real line. But you get a subgroup of R. But you see the point. So z cross z. If this is in pi 1 of m, and this is supposed to be sitting in, At this point, we have to use the fact that because the quotient, is a compact manifold, the group, this group is actually a discrete subgroup. Okay, and so if you had this z cross z, if alpha and beta, so alpha, beta, if one of them is hyperbolic, that would give you a discrete z cross z subgroup of R, right? By looking at this axis. So that can't happen. So of course we just need one of them to be hyperbolic. And so you conclude that the other one, so in fact you conclude that if there is a z cross z, then alpha is parabolic. See, as I said, there are no elliptic elements because there are no fixed points in the action of pi 1m. So therefore alpha is parabolic. Well, now the parabolic guys, if you now take a more convenient model now of hyperbolic space is to take the upper half space model. So in the upper half space model of H3, if you think of the point at infinity as being the fixed point of the parabolic element, so we take our three coordinate axes x1, x2, and x3, then a parabolic element is just conjugate to a Euclidean translation. And so in this model, so it's just so alpha is going to be conjugate to, x goes to x plus something, I don't know, maybe 0, well, 1, 0, 0, I guess. And so here's x and here's alpha x. But the point is that in this model of the hyperbolic, so the fixed point, this is a typical parabolic element. In this model, you see hyperbolic distances go to 0 as you go up, okay? Because the hyperbolic metric, I mean, you divide by the square of this coordinate. And so, so the distance between x and alpha x, the hyperbolic distance is going to tend to 0 as x3 goes to infinity. And so that means that you see, therefore alpha, well, I mean, the homotopy class, well, I guess alpha, right? When I'm thinking, okay, alpha is represented, see, alpha is represented by a loop down in the 3 manifold. I mean, this is going to correspond to a loop down in the 3 manifold. And so alpha is represented by arbitrarily short loops. But that's impossible in a compact manifold. I mean, right, so alpha would have to be trivial. So this is a contradiction since M is compact. Okay, so that's why that's why you can't have a Z cross Z. Now, I mean, just in passing, maybe let me remark that, in fact, you can also look at hyperbolic structures on manifolds that have sort of torus cusps. I mean, in other words, you can have parabolic elements, but the quotient won't be compact. So this is what happens with, for example, knot complements. The complement of a knot has this sort of torus cross R end, and many of them do have hyperbolic structures, and the parabolic elements will correspond to this, the Z cross Z, in those ends. But for a closed manifold, you can't have a Z cross Z. Okay, so that's a quick sketch of that argument. And the big conjecture of Thurston, all right, so let me leave this here. Okay, let me just erase this then. So in some sense, the second part of the geometrization conjecture is conjecture B, which applies, so this is Thurston's the main conjecture here. Is it the converse of this is true, right? So namely M an irreducible 3 manifold with pi 1 of M infinite. And no Z cross Z in the fundamental group, then M is hyperbolic. So he's basically saying that this rather obvious necessary condition is also sufficient. And the geometrization conjecture, you can think of it, I mean, it's just the combination of these two conjectures, A and B. This covers the case of finite fundamental group. This covers the case of irreducible with infinite fundamental group. Okay, so that's let me put that up. And then okay. So what about this? What about this business of Z cross Z's? So if you're hyperbolic, then you can't have a Z cross Z. Well, so what happens if you do have a Z cross Z? What do you expect then? So this is a good point to define the notion of incompressible surface. So let me do that. So again, so we've got a 3 manifold, and let's have some orientable surface F. So F is an orientable surface in some 3-manifold M. And one says, so it's a very important definition due to HUN, one says that F is compressible if there exists, say, a disk, which is called a compressing disk, D in M, such that D meets the surface F only in its boundary, the boundary of the disk, and the boundary of the disk is sort of essential on F. So the boundary of D does not bound a disk. Does not bound a disk in F. So that's, I mean, let me just sort of picture. So here's D, here's your surface F, and that would be a compressing disk, provided the boundary doesn't bound the disk. Okay. And some other point about this is that it's very useful. I mean, if you do have a compressing disk, well, you can compress it. I mean, you can sort of surger the surface along the disk. I mean, you know, you could then replace the surface by this. And that would be another surface which is simpler than the original one, and it probably still has some of the same properties that the original one had. And so if you've got something that's compressible, you can usually compress it, and so you have the notion of incompressible. So let's say that F is incompressible if F is not a two-sphere and is not compressible. We'll usually be dealing with irreducible manifolds, and so there aren't going to be any interesting two spheres anyway. Okay, so that's an incompressible surface. And, well, again, anyway, there's a... Okay, so incompressible surfaces, they were introduced by HUN. In fact, an irreducible manifold that contains an incompressible surface is called a HUN manifold. And there are many things that are known about HUN manifolds. But anyway, let me... at this point, I mentioned the analog of the sphere theorem for disks is called the disk theorem. Well, it should be called the disk theorem. So it's also called the loop theorem / Dehn's lemma or something. The history, you see, is very confused, and so the terminology got very confused. But this was also proved by Papakyriakopoulos. I'll just abbreviate him to... Story about Papakyriakopoulos is that when he was a young man, he said he wanted to achieve 3 things in life. I forget what they were. Wait. He wanted to prove the Poincare conjecture, write a book on 3 manifolds, and get married. So he never got past the first one, you know, so never got on. But he did prove, the sphere theorem, he proved this great Dehn's lemma. This disk theorem. It says that F in a surface in a 3-manifold incompressible. Again, it's one of these things that if and only if pi1 of F into pi1 of M is injective. So again, turning it around, it says that if pi1 of F into pi1 of M is not injective, then in fact there's a compressing disk, you see. So again, it's one of these theorems that turns, sort of homotopy theoretic information into very strong geometric information. To say that pi1 of F into pi1 of M is not injective says there's a singular disk, there's a map of a disk in. And what this theorem gives you is actually an embedded disk, see, a real live compressing disk, okay. So of course, one direction of this is obvious, but let's see, which one is it? That this direction's obvious, right? But because if you're compressible, then obviously pi1 of F is not injective. But of course, the hard part is the other way around. And this was the famous theorem that, well, pretty much. I mean, it's not quite this, but this was sort of, it's very closely related to Dehn's lemma. And this was the famous theorem that was announced by Dehn and had a mistake in the proof, which wasn't patched until 1957. So people thought that once this was proved, 3-manifold theory would be over. So it didn't quite happen. So maybe it won't be over. yeah, for another few years. Anyway, okay. But let me mention, why was Dehn interested in this? Well, he was interested in knots, right? I mean, who isn't, right? So let me just mention here a corollary of this, and this is really the corollary that Dehn was interested in. Well, one of the things, anyway. So if K is a knot in S3, then K is unknotted if and only if the fundamental group is Z. So the fundamental group of the complement. So this was really so let me just sketch the proof of this. I mean, it's very easy, but it's very, very sort of important historically. Well, I mean, of course, one way is obvious, right? I mean, you know, if it's the unknot, then but so the hard part is, again, using just the purely homotopic theoretic information to conclude very strong geometric conclusion that K is unknotted. Well, so the thing to do is to remove an open neighborhood of K. So, you know, you got K, and then you take some tubular neighborhood, N of K, and let's let M be the stuff outside, the so-called exterior of the knot. And so the boundary M, well, M is homotopy equivalent to the complement of K. In fact, the complement of K is just the interior of, homeomorphic to the interior of M. And so this is much more the pi 1 of M. And so if this is Z, right, then notice that the boundary of M, of course, is this torus, T2. Well, you know, the fundamental group of a torus is Z cross Z. The fundamental, if this is Z, then that implies that the map from pi 1 of the boundary into pi 1 of M is not injective, right? Because this is Z cross Z, this is Z. And so therefore by the theorem, by Papakouria-Kopas's theorem, then the surface must be compressible. I mean, I guess here I was sort of thinking of M as a closed manifold, and F is sort of sitting in, you know, in the manifold, but it really doesn't matter. I mean, you could take this boundary, you could push it into the interior a little bit if you wanted to, and so M doesn't have to be a closed manifold for this theorem to hold, and so we can apply it to this boundary, and so therefore boundary M compresses in M. And so you've got this compressing disk, so let D be a compressing disk for the boundary of M. And so let me go here then. So you see that now it's just a little bit of, I could have done. So somewhere on the boundary here, I mean, somewhere you've got this disk in M. So here's D. And the boundary of the disk lies on the boundary of M. And it's essential, it doesn't bound a disk in the boundary. But now you see, you just notice that, you know, it's clearly, I mean, this is null homologous, right? I mean, so this is 0 in H1 of M. Obviously, because it bounds a disk. It's actually null homotopic. And so therefore, it must intersect the meridian. So if this is the meridian, it must intersect the meridian once. So therefore, you know, the intersection number, the algebraic intersection number or whatever, is 1. And so you can make it actually 1 on the nose. And so therefore you can actually now just, so therefore there exists an annulus A in this neighborhood whose boundary consists of K, you know, together with the boundary of D. So you can actually span a little annulus across here. So with boundary A equal to K union boundary D, and so therefore now K bounds the disk D union this annulus A. So now you've got the knot bounding a disk in the 3 sphere, and so therefore it's the unknot. So that's a quick proof of that corollary. So that's just sort of in passing. That was why Dehn really proved his lemma. Okay, but So now we see that if you have incompressible tori, you see, in three models, they're going to be obstructions in general to having a geometric structure. See, so incompressible tori are in general going to be obstructions to geometric structure. So let me just take a very simple sort of class of examples. You know, you could take, for example, two knot exteriors. So let's say x1, x2, you know, exteriors. In other words, you know, of knots, of non-trivial knots, k1, k2 in the three sphere. Then as we've just seen, you see, then the boundary of xi is incompressible. If the knot's non-trivial, then the boundary of xi is incompressible in xi. And so if I form the manifold, let's say M, I just glue these two guys together along their boundary in any way I like, really. I get a closed manifold, and it contains this torus. So T is this common torus in M, and you see it'll be incompressible. Because it's incompressible in the two pieces. And also, again, because these are exteriors of knots in S3, by Alexander's theorem, see, xi is irreducible. And so therefore, when you glue two irreducible manifolds together along an incompressible surface, it's easy to prove that M is irreducible. In fact, that's another homework exercise for you. Okay. And so here we have, you see, so here we have this irreducible manifold. It has infinite fundamental group, but it contains this Z cross Z, you see, corresponding to this torus, this pi1 of T. And so it can't be hyperbolic, right? Because you can't have any Z cross Z's in a hyperbolic manifold. And, you know, there are so few Euclidean manifolds, there's only 6 of them. You can see that, you know, I mean, you'll never get a Euclidean manifold, you know, in this way also M, not Euclidean. I mean, we know all about that. And so here's a class of manifolds that, namely manifolds that contain incompressible tori. If you stay away from the Euclidean ones, then they can't possibly be hyperbolic. And so, well, so maybe that's the answer. Maybe as long as you stay away from incompressible tori. So again, let me write this up again. You see, so T incompressible torus in M, that implies that you've got a Z cross Z in pi1 of M, namely just pi1 of the torus. So this is, and so maybe the converse is true. So maybe this is the only problem, just incompressible tori. Well, it turns out that unfortunately not quite. So let me discuss this. So the answer is not quite. Okay. And again, this goes back to Seifert fibered spaces. Okay. So again, if we look at a Seifert fibered space, we have this. Remember the definition. It's made up of fibered solid tori. And the cores of these fibered solid tori, the core might be a sort of exceptional or multiple fiber, as Ron called it. But whatever, I mean, there's all these regular fibers. And so if you let H be the class of a regular fiber, see, they're all homotopic in pi1 of M, then it's easy to see that in terms of the fundamental group, you know, this guy generates a cyclic normal subgroup. In other words, HX inverse is going to be H to the plus or minus 1 for all X in pi1 of M. You see, it's very easy to see that the point is that when you have a Seifert fibered space, you have a certain finite number of exceptional fibers, and once you remove neighborhoods of those, what's left is just a circle bundle. So it's a circle bundle over some surface with boundary. And remember, I'm assuming that the manifold M is orientable. If the base surface punctured, and if it's, well, I mean, so it's just, you just have this circle bundle. So when you go around, some loop in the base, the fiber either gets left invariant if the loop is orientation preserving, or if the loop is orientation reversing in the base, it'll flip the fiber. And so that's where this comes from. And so, you've got, I mean, just think of H as being central, for example. In particular then, if pi1 of M is infinite, then, well, everything has infinite order. So this is now a sort of normal Z. And so you're going to get lots of Z cross Zs, right? So it implies that, lots of Z cross Zs in pi1 of M. Except, I mean, I'm lying a little bit. I mean, there's a couple of very special cases. I mean, there are a couple of very, very trivial Seifert-fibered spaces. It could be S1 cross S2, or, so just to be honest here, if M is not equal to S2 cross S1, or the manifold that's double covered by that, namely P3 cross P3. But if you stay away from these very simple cases, generically anyway, the point is that you've got lots of Z cross Zs in the fundamental group of a Seifert-fibered space with infinite fundamental group. Okay, well, do you have incompressible tori? Well, again, the answer is usually you do, but not quite always. And so at this point, there's a, let me quote the theorem of Waldhausen on incompressible surfaces in Seifert-fibered spaces. So, so M is Seifert-fibered space, then any incompressible surface in M can be isotoped to be either horizontal or vertical. Okay, so horizontal just means it's transverse to all the fibers. And vertical means that it's a union of fibers. And so, you see, usually you have vertical tori. I mean, let's just assume, for simplicity, I mean, assume that the base surface F is orientable. I mean, just to save writing some more cases. So you've got this orientable surface, this base of the fibration, and there are a certain number of singular fibers, exceptional fibers. The images are here. Well, you see, usually it's really easy. If the genus of F is greater than 0, I mean, you can find an essential loop in the surface. And so now, when you take the inverse image of that, you'll get a vertical incompressible torus. So if F is a sphere, is not a sphere, then you're happy. If F is a sphere, well, you've got some exceptional fibers. If you've got at least 4 exceptional fibers, you can still find a simple closed curve that has at least 2 images of exceptional fibers on each side. And so again, it's easy to see that when you take the inverse image of that, you get a vertical torus, incompressible torus. And so you get that. So usually these Seifert-fiber spaces do contain incompressible vertical tori, but I mean, you can see from this discussion that there are some that don't. So again, if I make this assumption, just for simplicity of statement there, so then M contains an incompressible vertical torus, unless well, unless, you know, the base surface is S2 and there's less or equal to 3 exceptional fibers. Now, of course, if there's so if I assume that pi 1 of m is infinite, which I guess, you know, I should have been doing here, right? Pi 1 of m infinite, right? So again, let me just assume that pi 1 of m is infinite, because that's the only case where it is. Then, of course, you can't have less or equal to 2 singular fibers. So, and there, so for these examples, these are really awkward. I mean, they come up a lot in various aspects of three manifolds, and they're sort of annoying, you know. They're just small enough that you can't really do too much with them. But anyway, but they're not too small either. So, see, there's no, any simple closed curve in the base is going to bound a disk containing just one, you know, the image of one exceptional fiber. So when you go up to the manifold, the corresponding vertical torus bounds a solid torus. Okay, so it's not incompressible. And so let's call those, well, let's call those small Seifert fibered spaces or something. And so they never contain verticals. Well, you say, well, maybe they contain horizontal ones, but let me not go into the details of that, but usually they don't. Usually does not contain a horizontal torus either. See, sometimes it will. For example, these Euclidean manifolds, they're all sort of bundles over the circle with fiber torus. So in fact, they do contain horizontal ones. But and you can say exactly when this happens. Anyway, so usually there's no horizontal tori either. And so we've got this class of three manifolds, and they're irreducible. They have infinite pi 1. They contain z cross z's in their fundamental group, but yet they don't contain incompressible tori. And so now we say, well, is that the end of the story? I mean, is that? And that is, in fact, the end of the story. You'll be glad to know. All right, so we're just about done. Namely, so let me just, okay, finish this. So there's the so-called torus theorem. We've had the sphere theorem, the disk theorem. Now there's a torus theorem, which again has a long history, which I won't sort of go into, but it was finally kind of settled in this form by Kassan and Jungreis, and independently by Gabay in the early 90s, that says that, so again, M an irreducible three manifold, and suppose there is a z cross z in the fundamental group, then, well, remember our first guess was that M contains an incompressible torus, and that would account for the z cross z. We saw that that's not quite true in general, but the other example, so or M, is a, well, small, you know, Seifert fiber space. So that's the end of that story. And again, Seifert fibered spaces we understand well. And as I say, if you kind of extend your definition of geometry to include some other geometries which are not, what did I say, isotropic or something, then in fact all Seifert fibered spaces are geometric in this more general sense. And so the upshot is, you see, that either you're a Seifert fibered space, well, assume you're irreducible, right, which we might as well. Either you're finite pi 1, in which case you're probably spherical, that's a conjecture, or you have infinite pi 1, and you don't have any z cross z in your fundamental group, and there the conjecture is you should be hyperbolic, or you do have a z cross z, in which case you either have an incompressible torus or you're one of these small Seifert fiber spaces. So finally, let me just finish off by just making some remarks about the sort of more general sort of geometrization sort of conjecture, I mean, which is sort of known. I mean, it was known before Perlman. I mean, this is the Jsj decomposition. And so again, you know, we had Kneser's theorem, which said that you could take an arbitrary three manifold and cut it along spheres into prime pieces. You know, it was a connected sum of prime manifolds. So this Jsj decomposition, I mean, in its most elementary form, it's not so difficult, and it deals with cutting along tori. And so we've seen that, you know, incompressible tori play a sort of important role in this question of whether or not your manifold's geometric. So again, you know, M is a closed orientable 3 manifold. So maybe I'll just state the theorem. Let me just state the theorem because I don't have too much time, maybe. And so it's actually irreducible. So let me just state the theorem here. Okay. So here's the theorem. And this is due to Jsj Johansson. No, sorry, Jacob-Shalen Johansson. Okay, Jacob-Shalen Johansson. Okay, Jsj, right. They sort of prove much more than this, but in this form it's really not that difficult. But as I say, they actually prove much more. But so again, M is a closed, orientable, irreducible 3 manifold. So then there exists, okay, so then there exists this collection, a disjoint union, a finite disjoint union, let's call it sort of script T of incompressible tori in M. And it's canonical, it's sort of unique up to isotopy. So it's really this such that each component of M cut along, when you cut the manifold up along these tori, each component is either, well, it's either atoroidal So that means that any incompressible torus is parallel to a boundary component. Now you see, if you have a closed manifold, I guess you say it's atoroidal if it doesn't contain any incompressible tori. But if you have, for example, a not exterior, then of course there is an incompressible torus, namely the boundary. But again, that's a sort of trivial incompressible torus. So in general, you say a manifold with boundary is atoroidal if the only incompressible tori, you know, come from boundary components. Either atoroidal or a Seifert fiber space. Or possibly both, of course. And you think, and T is minimal with respect to this property. Well, I mean, let me not even say that. I mean, that's how you get the uniqueness. Well, sorry. Okay. No, T is minimal with respect to this property. So let me just make some couple of concluding remarks, if you don't mind. Sorry, I'm running over a little bit, but see, what Thurston proved is that if this collection is non-empty, see, of course this collection might just be empty, in which case it's not really saying very much. You just get some atoroidal manifold. Well, there you go. But if this collection is non-empty, then the atoroidal pieces, then the atoroidal non-Seifert fibered pieces, you know, non-SF pieces are hyperbolic. In this sort of generalized sense that, you know, you allow sort of cusps, you allow parabolic elements in the group. But so this is somehow this was. I mean, this is sort of the geometrization conjecture. I mean, that you can cut the manifold up. First of all, you cut it along spheres into irreducible pieces. Now, the irreducible pieces you cut along tori. And if the collection of tori in question is non-empty, then everything's understood, you see. So the only cases that are left are the cases I mentioned, you know, conjecture A and conjecture B. And so they may or may not be solved. But that's sort of the picture. Let me just say one thing about, final remark about this theorem. You see, it's easy to see that you can always cut the manifold up into atoroidal pieces along tori. Well, I mean, it's perhaps not that easy, but it was classically proved. There's a theorem of HUN which says that in a closed three-manifold, you can only pack in a finite number of non-parallel incompressible surfaces that are disjoint. A beautiful argument that goes back to Knaser, actually. I mentioned Knaser. The same way that Knaser proved the existence of the prime decomposition, you can use the same idea to prove the so-called HUN finiteness theorem. So, you know, you can always cut the manifold up into atoroidal pieces by cutting along a certain disjoint collection of tori. The thing is that that's clearly not canonical, see? Because a simple example, if you take a surface cross S1, right? I mean, you can cut the surface into sort of pairs of pants, you know, into three punctured spheres along simple closed curves. I didn't need that one, did I? Okay. So if you cut this three-manifold along the corresponding sort of vertical tori, then you're cutting it into atoroidal pieces. Well, fine. But you see, these curves, I mean, there's infinitely many choices of these curves, and so there's clearly infinitely many ways of cutting this manifold up into atoroidal pieces by incompressible tori. So the great observation is that, well, this is a Seifert-Fibert space. And so the great observation is that don't cut it into atoroidal pieces. Cut it into pieces that are either atoroidal or Seifert-Fibert. In other words, amalgamate as many as you can into Seifert-Fibert pieces. And all the non-uniqueness is concentrated in the Seifert-Fibert pieces. So just don't worry about that. And now when you do that, you see, then it's quite easy to prove that this collection is actually canonical. So that's sorry. Anyway, okay. That's next time I'll start talking about Dehn surgery, and the idea there is we're going to be looking at typically a hyperbolic knot, say, and we're going to be doing Dehn surgery on it, and we're going to say, well, most of the time you get a hyperbolic manifold, but sometimes you don't, and so that's partly why I gave this discussion here, because you may get a Seifert-Fibert space, you may get a lens space, you may get S1 cross S2, you may get something that has a torus in it, you know, and so we'll discuss those various cases. All right.